I'm Henry Gilliland, the mechatronics specialist with Electric Supply and Equipment. In this video, I'm going to explain the purpose of the MAM instruction and show you how to properly implement it using ladder logic in Rockwell's Studio 5000 Logix Designer. But before we get going, please be sure to subscribe to ES&E TV to view more videos like this one. The MAM, or Motion Axis Move instruction, is the integrated motion instruction that's used to move a given axis to a specific position. This means that when an MAM is executed, the axis will use a motion profile defined by the instruction fields in order to move to a desired position. Let's take a look at the different components of the instruction. First, you have the axis field. This is where you will assign the axis that the instruction will target. Next, we have the motion control field. This is where a tag of type motion instruction will go. This is the tag that will be used by the processor to perform the functionality of the whole instruction. Next, there is the move type field. This field is used to define what type of position move the instruction will perform. Next is the position field. This is the field that defines where the axis will move. The value in this field can mean a number of different things, depending on which move type is selected. The units of this field are defined by the scaling of the axis, which can be changed in the axis properties. Next, there are the speed and speed units fields. These are used to specify the speed at which the axis will move when it is moving to the target position. Then there is XL, XL units, decel, and decel units. These fields allow you to adjust the rate at which the axis will ramp up to the target speed. When the target position is about to be reached, the motion planner in the PLC will use the value set in the decel field to identify when the axis should begin to ramp down. The planner will ramp the axis down and stop just in time to reach the target position. The profile and jerk fields allow you to control the XL and decel ramp. By adjusting jerk or S-curve, you can adjust the rate of change of acceleration. We'll discuss that further shortly. The merge and merge speed fields allow you to take over full control of the axis with this MAM instruction. If merge is enabled, then any other currently running motion instructions will be stopped, and this MAM will control the action of the axis going forward. The lock position and lock direction fields are used for coordinated movements between axes. Most of the time, these fields aren't used with the MAM instruction. The last two fields are called event distance and calculated data. These fields can be used to capture motion planner information about the move that is currently being executed. These fields take array tags of type real. The event distance array is used to define positions where the time from the end of the move will be calculated. This timing data will be stored in the calculated data array. If these fields are set to 0, then they won't be used. Then there are 5 status indicator bits. None of these bits tell you anything about the current state of the target axis. They're only diagnostics associated with the given instruction. The EN, or enable bit, will be true when the rung that the instruction is on goes true. The DN, or done bit, will be true when the motion instruction executes successfully with no errors. The state of the done bit only updates when the enable bit transitions from false to true. The ER, or error bit, will be true when the motion instruction executes with errors. The state of the ER bit will also only update when the enable bit transitions from false to true. The IP, or in process bit, will be true while the instruction is currently running a task and has not yet finished. The PC, or process complete bit, will be true when the instruction reaches the target position. As a note, the PC bit will also only change states when the enable bit transitions from false to true. Now let's build the instruction in ladder logic. You can find the MAM instruction under the Motion Move tab of the Ladder Logic Instruction Selector. Assign the target axis, then create an instruction tag. It's a good idea to name the tag after the instruction itself. That way, when troubleshooting in the future, it'll be easier to find the tag. Now right-click on the label and select New in order to create the tag in the tag database. As mentioned earlier, the tag will be of type motion instruction. Select Create. Now we will need to fill in all the fields of the instruction. I find it helpful to start by selecting the units of each field first. It's important to note that the pre-configured scaling is set on the Scaling tab of the Axis properties. In this case, the units are defined as degrees. Now we know that when the instruction says the word units, it means degrees for this particular application. Now let's go back to the instruction. For speed units, I recommend selecting units per second. Again, in this case, this means degrees per second. For XL and decel units, I recommend selecting units per second squared. For jerk units, I recommend selecting percent of time. In this example, we will not be using the merge or lock position functionality. When not using this functionality, it's recommended that you set merge to disabled, set merge speed to current, set lock position to 0, and set lock direction to none. We will also not be using event distance or calculated data, so we'll set both of those fields to 0. Now go back to the top and select the move type. Let's discuss the different options. 0 means absolute move. This means that the instruction will move the axis to the position specified in the position field. For example, if the current position is 10 and the position field has a 5 in it, then the axis will move in reverse 5 units and the final position will be 5. 1 means incremental move. This means that the instruction will move the axis a distance specified by the position field and referencing the current position. For example, if the current position is 10 and the position field has a 5 in it, then the axis will move 5 units and the final position will be 15. There are several other more advanced options that are beyond the scope of this video. For more information about how to use these options, you can consult the instruction help file. We will select 0 for an absolute for this example. Quick tip here. If you hover your mouse over the field you would like to edit, the bottom left-hand corner of the Logic Designer window will show a note that helps with the current field. In this case, it clearly tells us 0 means ABS or absolute, and 1 means INC or incremental. Now let's discuss how to define the dynamics of the move. Using a tool like Motion Analyzer Online is helpful here. There's a link to this free tool in the description below. For this example, we want to move the servo 360 degrees from 0 in 1 second. Using an index profile, we can generate the information we need. Add the index profile, then set the motion time to 1 second and the motion distance to 360 degrees. To add in S-curve, simply apply a value in the jerk field. Entering 50% jerk means that the profile will use 50% of the move time to ramp the acceleration. However, with jerk set to 50% of time, we can see that the acceleration needs to be higher in order to reach the target speed in the same amount of time. We will set the decel jerk to 50% of time as well. It's generally a good idea to use jerk in all your moves. Adding jerk, or S-curve as it's sometimes called, puts less wear and tear on your mechanical system and allows for greater control over the moves. Now let's gather the calculated data we need to enter into the MAM fields. As we said, our target position is 360 degrees. We can see that our target speed will need to be 540 degrees per second. The XL and decel need to be 2,160 degrees per second squared. And finally, we can set our jerk to 50% of time. Now your move should be completely filled out and ready for testing. We can now compile the code. In order to execute the instruction, the rung the instruction is on will need to transition from false to true. However, this instruction will only work properly if the target axis is not faulted and is currently in the running state. you can use the MSO instruction to put the axis in the running state. Once the axis is in the correct state, we can toggle the bit on the rung. As you can see, when the rung is true, the enable bit is true. This instruction executed successfully, so you can see that the done bit is also true. You can also see that the in process bit turned on and then back off when the instruction finished. When the instruction finished, the PC bit turned on. When the MAM is executed, the motor being controlled by the target axis will ramp up to speed using the defined parameters until it reaches the target speed. Then, when the axis is about to reach the target position, the axis will automatically ramp down the speed to stop exactly on the target position. You can see this happen here. The wheel turns 1 revolution, or 360 degrees. This move can be edited to run the axis back to 0 by changing the target position back to 0. You will see that the wheel rotates in the reverse direction 1 revolution back to 0 degrees. If the error bit turns on when the instruction is executed, then you can examine the error code stored in the instruction tag and use the instruction help file to troubleshoot the error. Now you know the basics of how to properly use and configure the motion axis move instruction. If you liked this video, please click the like button and the notification bell so you'll be notified when we post new videos. Thanks for watching.